Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss classical Langevin theory of diamagnetism. Let's begin. Diamagnetism is observed in all those substances in which atoms have even number of electrons around the nucleus. Atoms have even number of electrons around the nucleus. Those substances are known as diamagnetism. If there will be odd number of electrons, then it will be treated as paramagnetism substances. What that particular theory indicates, according to this theory, the diamagnetism could be traced to the orbital motion of the electrons, and the change in that of orbital moment induced by an applied magnetic field that explains diamagnetism. And that theory of diamagnetism was first explained by the scientist Paul Langevin. The atoms which has even number of electrons around that of nucleus are considered as diamagnetism, and these electrons, when motion around that of nucleus, they execute the magnetic moment, and the net magnetic moment, or we can say the change in orbital moment, due to that of applied magnetic field, that explains the diamagnetism property of that material. Let me understand it by using an example. For our simplicity, let me consider an atom, that atom having 2 electrons. 2 electrons means it is even. These 2 electrons move around the nucleus with the same speed on same orbits, same speed on like orbits, but in opposite directions. As their spins are different, one is up and another one is down, so the electrons move around the nucleus with the same speed on that of same orbit, but in opposite directions. That be the nucleus. Around that of nucleus, electron is revolved. Let it as the velocity v, omega, the angular velocity, another electron move on that of same orbit, but in opposite direction. Opposite direction. The orbital magnetic moment of one electron is equal but opposite to that of orbital magnetic moment of the second electron. Hence, the total magnetic moment of that atom is 0. Therefore, we say the diamagnetic substances have zero magnetic moment. Since the diamagnetic substances have even number of electrons around that of nucleus, one electron have that of orbital magnetic moment and another electron have the same orbital angular moment, same orbital magnetic moment, but with opposite direction. What it say? Electrons revolve around that of nucleus. So, the revolving electrons constitutes current. As we say, the direction of current is opposite to that of direction of flow of electrons. Therefore, in that of circuit, in that of orbit, the flow of current is just opposite, and flow of current nothing but it constitutes the production of magnetic field, and that magnetic field we say that if we observe it in that of upper phase, we say that electron just like as the north pole, and we observe it in that of lower phase, they just look like that of south pole. Means in that of section, that electron just treat as a magnetic dipole. Same situation also happen here. If one phase is south, another one is north, and at that of situation, that electron also referred as a magnetic dipole having north and south pole. Here the magnetic dipole moment, let mu e, the magnetic dipole moment, the direction of magnetic dipole moment is what? That case it is its opposite but equal. The magnetic dipole moment, since upper one is north, lower one is south, here upper one is south, lower one is north. So, the direction of induced magnetic dipole moment in these two cases are just opposite. So, the net magnetic dipole moment in that of atom will be 0. So, therefore, we can say in diamagnetic substance it has 0 magnetic moment. So, mathematically let I, that is the electronic current, R radius of orbit here we assumed it is a circle, assumed to be circular, but actually it is elliptic, actually it is an elliptical one. Then the magnetic dipole moment, of each electron is given by mu m, that is current into area, mu m is equal to current area as pi r square, or mu m, here current, charge by time period, E by t into pi r square. So the time period mu m is equal to E divided by 2 pi divided by omega naught. Omega naught is the angular velocity of one electron. Omega naught, that is the angular velocity of one electron, pi r square. Therefore mu m is equal to half E omega naught r square. It is the magnetic dipole moment of one electron. Therefore the net magnetic dipole moment, therefore the net magnetic moment of the atom due to one electron, it is half E omega naught r square. Due to another electron, the magnitude is same, but it will be in the opposite direction. Therefore we prefer as a negative sign, minus half E omega naught r square. So finally we obtain mu m, net magnetic dipole moment of the atom, will be 0. Hence net dipole moment of the atom in the absence of any external magnetic field is 0. The net dipole moment of atom in the absence of any external magnetic field is 0. So when there will be the absence of external magnetic field, in the absence of external magnetic field, the centripetal force required by the electron that is provided by electrostatic force of attraction between the nucleus and the electron. The centripetal force is equal to m v square by r. V is the speed of that electron, r is the radius. In place of v, as we know, v is equal to r into omega naught m r square omega naught square divided by r, which is equal to m omega naught square r. that is the centripetal force m omega naught square r, and that centripetal force is towards the center of that of orbit. It is positive. The direction of centripetal force is towards the center of the orbit. It will be happen when there will be the absence of external magnetic field. So, the net dipole moment inside that atom will be 0 and the centripetal force is equal to m omega naught square r. But when we apply an external magnetic field, then what happened? Now, let us apply an external magnetic field that is B is equal to mu naught H, such that the applied external magnetic field this field is perpendicular to the plane of the orbit of electron. And when that external field is applied, then additional force acts on it due to that of Lowrance force. When an external field is applied, then an additional force f of b, and that force we say that is Lowrance force, which is equal to E v b, charge into velocity magnetic field. E dot v cross b, v b sin theta, here angle between v and b is 0 degree, sin 0, sorry, v and b are perpendicular, sin 90 1, E v b, that force acts on it. And the direction of Lowrance force depends upon the clockwise or anti-clockwise rotation of that of electron. Therefore, the new centripetal force is equal to centripetal force in absence of magnetic field plus or minus, that depend upon either that electron is clockwise or anti-clockwise, plus or minus Lowrance force. Therefore, for two electrons in that of two orbits, in one orbit, the moment of that of electrons both are opposite in directions. Therefore, the centripetal force, the expression for centripetal force m omega square r, here mass for first electron, let omega 1 square r is equal to centripetal force Fc minus E V1 B, and another electron m omega 2 square r Fc plus E V2 B. Now, these expressions can be written as, now m omega 1 square r is equal to Fc minus E V1 B is equal to, in place of Fc we substitute m omega naught square r minus E V1 B is equal to or m omega 1 square r is equal to m omega naught square r minus E, that velocity as omega 1 into r into b, as V1 is equal to r into omega 1 or m omega 1 square r. Let r be taken as common on both sides and r cancelled out, so it will be m omega naught square minus E omega 1 b is equal to omega 1 square is equal to omega m divided on both sides, so omega naught square minus E omega 1 b divided by m. Let equation number 1. Again, taking that equation as m omega 2 square r is equal to Fc plus E V2 B, or m omega 2 square r is equal to m omega naught square r plus E V2 B in place of Fc, that is m omega naught square r, or m omega 2 square r is equal to m omega naught square r plus, in place of V2, E r omega 2 b V2 r omega 2, velocity for second electron, or r on both sides common and cancelled out, m omega 2 square is equal to m omega naught square plus E omega 2 B, or omega 2 square is equal to cancel out, it will be omega square plus E omega 2 B divided by m. That equation number 2. Now subtracting equation 2 from equation 1. Subtracting equation 2 from 1, we get omega 1 square minus omega 2 square is equal to minus EB by m omega 1 plus omega 2, a square minus b square, a plus b whole into a minus b formula, omega 1 plus omega 2 omega 1 minus omega 2 is equal to minus EB by m omega 1 plus omega 2, omega 1 plus omega 2, omega 1 plus omega 2 cancel out on each side, omega 1 minus omega 2 is equal to minus EB by m omega 1 minus omega 2, that is change in omega, del omega is equal to minus EB by m. That is equation number 3. That is the change in frequency is equal to minus E by E B by m, that is known as this equation is known as Lamar theorem. And that frequency change is known as Lamar frequency. But our task is to calculate the magnetic moment of that of electron. Therefore, magnetic moment of electron is given by mu m is equal to E omega r square divided by 2, and change in magnetic moment due to change in omega, that is let del mu m E by 2 change in omega del omega r square, or delta mu m is equal to delta omega value is put here, so minus E by 2 E b by m r square, or delta mu m is equal to minus b e square r square divided by 2m. The equation number 4. This change is actually the relative change in dipole moment of two electrons due to the change in their angular velocity. The change in their angular velocity. If del mu m dash is the change in dipole moment of each electron, then del mu m is equal to del mu m dash minus of del mu m dash, or del mu m is equal to del mu m dash plus del mu m dash. Del mu m is equal to 2 times of del mu m dash, or del mu m dash is equal to del mu m divided by 2, or del mu m dash is equal to, putting that value, del mu m as minus b square r square divided by 4m, 2 into 2 4, del mu m dash is equal to minus value of b as mu naught into h, so mu naught e square r square divided by 4m into h, and the external magnetic field B is equal to mu naught into h, and equation number 5. If we consider, now we consider the induced magnetic moment of whole of the atom instead of an electron. Instead of an electron, we preferred for whole of the atom, then mu, the total induced magnetic moment, sum of del mu m dash, which is equal to minus mu naught e square r square, sorry, e square h divided by 4m summation over r square, because summation over r square, that is the mean square distance of each electron from the nucleus. If since the electrons, that is the nucleus at the orbit, and the electrons revolve around that of orbit like this way, therefore we prefer the mean square distance. If x, y and z are the coordinates of radius r of the orbit, then r square is equal to x square plus y square plus z square. If that is the spherical symmetry, for spherical symmetry x square is equal to y square is equal to z square, that is r square divided by 3, taken it in as spherical symmetry. Further, if the z axis is chosen to be in the plane perpendicular to the applied magnetic field, then summation over r square as x square plus y square. Since we choose z axis which is to be plane perpendicular to that of applied magnetic field, therefore summation over r square in place of x square, r square by 3 y square as r square by 3, that is summation over r square is equal to 2 times r square by 3. The equation number 7, and that value is put to that of equation number 6. Putting this value, in equation number 7, putting this value in equation number 6, we get mu is equal to summation over del mu m dash is equal to minus mu naught e square h divided by 4m into, in place of summation over r square, it is 2 by 3, again summation over r square, two by 3 r square, or mu is equal to minus mu naught e square h divided by 6m r square. Equation number 8. If there are n number of atoms per unit volume and Z is the atomic number of atom, then the intensity of magnetization I is given by intensity of magnetization I is equal to n z mu, or I is equal to minus n z mu naught e square h r square divided by 6m, the intensity of magnetization. From that of relation, we also calculate the diamagnetic susceptibility. Hence, diamagnetic susceptibility xi m is equal to I by h xi m is equal to minus n z mu naught square divided by 6 m equation number 10. This is the classical Langevin results. This is the classical Langevin result. From this, it is clear that the magnetic susceptibility is independent of temperature. The classical Langevin result, the magnetic susceptibility is independent of temperature. So here we show, first of all, how the net dipole moment will be 0 in the absence of external magnetic field, and the centripetal force, the magnitude of centripetal force and its direction. If we apply an external magnetic field, the application of external magnetic field, that is B is equal to mu naught S, at that of situation, the new centripetal force will be centripetal force in the absence of magnetic field plus minus the Lowrance force, and that plus minus is depend upon either the electron is clockwise or anti-clockwise. And change in the delta omega is equal to minus E by EB divided by m, which is the Lamar theorem. So the change in magnetic moment due to the change in omega is calculated. Accordingly, you have to calculate del mu m dash, then induced magnetic moment whole of the atom. Next, for summation of r square, we prefer it as a spherical symmetry system, and then it is calculated, and that value is put it. We finally obtain for mu, then I, then xi m. So with the help of this video lecture, we understand the concept of classical Langevin theory of diamagnetism. As an example, taking a simple atom having 2 electrons, we show it mathematically. So with this useful and informative notes, let me wind up this session. Thank you.